Do you want to turn this off? Maybe maybe turn the mic off.
This is a microphone, right?
For Zoom, this is for Zoom. Right.
So I have to put somewhere here.
Sorry,
I have to hold it or,
I put it on my.
okay.
If you flip it high enough on your
Mm,
Maybe a little higher.
okay.
Yeah.
Maybe I can, okay. Let me just put it inside. Oh, it's a lot of work.
it's too not works for us.
Yeah, this one cannot work.
Battery
Okay.
Yeah, all right.
Okay, perfect.
All right, no further ado. Well, take it away. Thank you.
Okay. Can you hear me now? Okay. Thanks a lot for this kind of introduction. I'm currently a postdoc from Technology University of Darmstadt. So actually, we have been working on this topic, dislocation-tuned functionality in Ferroelectrics for several years. But today, I would like to show you some results about the anisotropy and its applications. So we know that dislocation are 1D defects, and they are the Mercurial plus deformation, so which can largely affect the classical mechanical properties of many materials. So dislocations in ceramics can provide strain fields. And they can also be charged and form the space charge layer. We know that domain walls can be considered as 2D defects in ferroelectrics. For example, the 90-degree domain wall and the 180-degree domain wall. Now, if we put dislocations into ferroelectrics, we may be able to control the mobility of domain walls based on the dislocation domain wall interactions. So first, I will briefly introduce the background and the motivation. Then I will show you the concept that we call the dislocation imprint and the opportunities for band entitlement. After that, I will show you two examples by loading along two different directions and show you the influence of dislocations on properties. Finally, I will summarize my talk. So let's start with the possible effects of dislocations in ceramics. As I mentioned earlier, dislocation can pin the domain wall motion when we apply electric field. So if we design some spatial rings, we can induce ferroelectric phase out of the relaxer matrix. Dislocations themselves can actually act as these scattering centers and the conductive paths for surface reactions. So more important, dislocations are immobile at least up to 600 degrees Celsius as compared to the chemical doping. So our motivation to make materials by mechanics and not chemistry. So the material system that we select is the single-crystal badminton titled because it's the ferroelectric mode system and it has only 180-degree domain walls and 90-degree domain walls. So you may think badminton titled single-crystal operate in nature at room temperature, but now we are able to nicely deform the badminton titled single crystals by loading along two different directions to activate the two different sleep systems. For example, loading along the 001 direction will most likely activate the 110 sleep system. While loading along the 001 direction will activate the 100 sleep system. Here, I would like to emphasize that for both cases, we could have the sleep plans with the maximum Schmidt factor 0.5. But for the 100 sleep system, it can only be activated at high temperatures. So if we consider the domain distribution in the single crystals, there are a lot of opportunities for us to tune the properties. So the first example that I want to show you is the 001 loading. So basically, we have the single crystal and we just compress this single crystal along the 001 direction by using the high temperature grip experiments. So after the deformation, we see some cloudy regions with 45 degrees and with respect to the edges. In this case, we know we activate the 110 sleep system as schematic shown here. And if we closely look at the domain structures, we see some changes. So we are very interested in to see the influence of dislocations on properties. And therefore, we made the converse parallel coefficient D33 star as a function of the electric field. We see something very interesting. When the electric field is low, the D33 star is almost constant. When the electric field is higher than a certain value, we see large increase in D33 star. And compared to the initial value, the D33 star at about 50 volt per millimeter increase about lighting times. So what could be the mechanism underlying the large increase in D33 star? So we think at the first. So when we introduce dislocations into the single crystals, we will introduce the local energy potentials. When the electric field is low, the domain walls can be pinned by dislocations. If we apply electric field higher than the pinning field, the domain walls can go across the dislocations, and this will largely contribute to the displacement of the enter sample. So the local dislocation domain wall interaction plays an essential role for the enhancement of the D33 star. But we believe that the changes in the D33 stars should be related to the domain ratio. So therefore, we checked the domain ratio by using the NMR technique. And we found that for the reference undeformed sample in the paired state, it has only C domains, while for the deformed sample in the paired state, it has AC domains. In this case, the microscopic restoring force will ensure the reversibility of the D33 star. So based on this work, by using the mechanical dislocation imprint, we can basically control the polarization and the domain structures and enhance the pattern response. From our mechanical perspective, it's easy for us to have the idea for the 1D and 2D defect interactions. Basically, we could have two cases. The first one is the intersection case. We have the dislocation flows into the 2D domain wall, and the second case is the parallel case. We have the dislocation which is parallel to the 2D domain wall. So what we can expect is that the local pinning force should be largely different for both cases. So when we had this design strategy, and our collaborator, Dr. Zhou from Sichuan University, he did the phase field simulations. And for the intersection case, the local pinning force is only 0.2 newton, while for the parallel case, the local pinning force is 3.2 newton. So which confirm our design ideas. And he also calculated the local energy potential as a function of the domain wall position. When we apply small electric field, we can largely change the energy profiles. It means that we may be able to further enhance the properties and also design the isotropic electric properties. So we deformed the sample along the 110 direction, and we want to activate the 110 slip system by using the high temperature plastic deformation at 1150 degrees Celsius. So you can basically see the textbook like straight strain curve, and with the clear, oh, sorry. Oh, okay. And with the elastic deformation region and the plastic deformation region. So the plastic deformation will contribute to the introduction of dislocation into the barometric single crystals. If we check the optical images, we see some changes in the domain patterns. So here we want to investigate the dislocation based on anisotropy. Therefore, we cut the sample along two different directions. For the upper part, we call 110 cut samples, perpendicular to the 110 direction. For the bottom part, we cut the sample parallel to the 110 direction. We call the 001 cut sample. So our TEM results suggest that most likely the dislocation are parallel to the 001 direction, which confirms the activity of the 10010 slip system. So the next step is to establish the base for the 1D, 2D defect interactions. So for 001 cut deformed sample, we apply electric along the 001 direction, which means parallel to the dislocation lines. Well, for the 110 cut deformed sample, we apply electric field parallel to the 110 direction. It means perpendicular to the dislocation lines. So it's actually a very nice platform for us to quantify the electric properties, both perpendicular to and parallel to the dislocations. We first measured the P loop at room temperature, and we found that for both cuts, the deformed samples, the maximum polarization and the minus polarization reduced while the EC increased. So I would say we already successfully introduced dislocation in the both cuts. We also simultaneously measured the permittivity and the distribution as a function of the AC fields. So here, for the 110 cut deformed sample, we can even get high distribution values that we used by loading along the 0 direction. And we can also get much high permittivity. It's also very interesting that when we look at the properties during the increasing and the decreasing AC field process, for the 110 cut, both properties go anti-clockwise, where for the 0 cut deformed sample, the properties go clockwise, indicating that the clear anisotropy, and also it's a sign of the dislocation-induced different stability. In order to determine the dislocation-based stability, we just continue the measurement and record the properties up to about 6 hours, in total 19 cycles. So for the 0 cut deformed sample, we have the intersection configuration. So if you look at the properties for both properties, we see the clear degradation at the beginning. Where for the 110 cut deformed sample, we see much stable properties. So if we plot the properties at 50 watt per millimeter, we can clearly see the difference. So what could be the mechanism for the different stability? Therefore, we also use the NMR to determine the domain ratios in the intersample. For example, the 0 cut deformed sample, we have the intersection case, and after the polling, we have a large amount of C domains, where after the second measurements, we have only a small amount of C domains. So the unstable domain structures is responsible for the unstable properties. When we check the domain ratios for the 110 cut deformed sample in the paired state and the cycled state, they're quite stable. So with this, I would like to conclude my talk by using the concept of dislocation influence. We can control the polarization in bulk ferroelectrics, which was confirmed by two loading conditions. And the dislocation-based anisotropy is also a very nice concept for us to train the properties. Finally, I would like to thank the DFG project and the Honest Humboldt Foundation to support this work. Thank you very much.
Thank you, Master. Okay, for the raise. And about the permittivity data, a function of basic function. So look like it's funny shape. I think it's for the behavior, right? So I think we can interpret it as